Hi everyone, my name is Talha.
I'm Ryan.
I'm Annie.
And I'm Stephen. Today we'll be presenting our project for APS360, which is focused on classification of geographical landmarks. Landmark classification is an important task, as it allows people to learn more about culturally relevant areas of interest. If you ever go traveling and you see a beautiful building, a good landmark classification system can answer any questions you have about that landmark. Landmark classification is a popular machine learning problem, in no small part due to its difficulty. Compared to standard image classification problems, landmark classification has a few eccentric nuances. First and foremost, the dataset is really sparse. Landmark data is hard to collect and prune, so most landmarks only have a handful of examples. This few-shot learning environment makes it important to learn crucial features both quickly and efficiently. Another issue is that there are a lot of classes. The dataset that we use, the Google Landmark Recognition dataset, has 81,000 classes distributed across over 1 million training examples. As a result, we'll need to utilize large models with enormous layers to adequately classify everything. Finally, the samples can vary significantly even within a single class. So for example, look at the images on this slide. Despite their differences, they actually correspond to the same landmarks. Before we talk about how we address the above problems, we should talk about the data. I'll hand it over to Talha to discuss data processing.
Thanks, Stephen. So we opted to simplify the problem by creating a smaller subset of the data. This is because the original dataset is 105 gigabytes, which is far too large for us to train. However, we opted to preserve the relative sparsity of data in order to keep the difficulty of the problem intact. We thus created a dataset of the 1,000 most frequent classes in the larger dataset, selecting only 5 images per class. The number of samples per class has been homogenized in order to avoid difficulties with imbalanced datasets, namely poor precision and recall. We had a 75-15-10 train validation test split. This was chosen to maximize the amount of data available for training due to the lack of images per class to begin with. For the actual data processing pipeline, we opted for a conventional set of transformations that are compatible with many pre-trained models. Firstly, we applied the standard center cropping and reshaping to 224 by 224. Then, at train time, we randomly applied affine transformations and color distortions. This is important for 2 reasons. First, this effectively provides us with more data, which helps to address the sparsity issue. Second, the data augmentation helps us account for common quirks in images. Affine transformations address images that were taken at different angles, while color distortion allows us to effectively ignore the time of day at which the image was taken. So for an example of our data processing, look at the images on this slide. The top row consists of the raw images, while the bottom row is potential processed images that were fed into our model. So now we're going to talk about our model, or should I say models. Take it away, Annie.
Will do. Instead of using a single model, we created an ensemble of 3 models with diverse architectures. Our first model is EfficientNet B0, which is a deep CNN with 278 layers and 4 million parameters. Our second is Squeeze Excite Residual Net 50. This network, which is also a CNN, is considerably denser with 26 million parameters in 270 layers. The third part of our ensemble is called a Tiny Swing Transformer with 28 million parameters in 223 layers. The way an ensemble works is that each model makes individual predictions for what a landmark could be, and then the most common prediction is taken as a final output. So each model, which is trained separately, will contribute to our solution. This ensemble will be compared to the baseline model, which is a normal residual network whose embeddings are transformed to a SVN for classification. We train our models by doing a grid search over a select range of hyperparameters after tuning the number of epochs and optimizer separately. We tune batch size, learning rate, freezing the pre-trained weights or not. We opt to keep hyperparameters related to model architecture unchanged since these have been meticulously tuned already. I think it's a good idea that we demo this model so that we can get an idea of how exactly it works. I will hand it over to Ryan to do that.
Thanks, Annie. So now we'll be moving on over to the demonstration. So here's our demo. It's a Jupyter notebook, and we're going to start off by running all of the precursor code and loading in our networks, starting up our K9 classifier and loading in our embeddings. Now we're going to look at 2 different images here, where one is a positive example where the model managed to get it correct. These 3 rows represent the top 5 predictions from each of our 3 ensembled models. So the top is EfficientNet, middle is SENet, and bottom is the Swin transformer. Here in the incorrect prediction, we can see that although these do not correspond to this class. We can see that some features are shared throughout all of these images, such as the concrete floor, that's the paved floor that's seen in the original image in all of these images. So it means that the models did pick up some relevant features, although it wasn't enough to identify the landmark. Now we're going to apply our data on data that we collected. So we went out to Haultain and we took some pictures, and we're going to add 5 of these pictures to our Cannon model. And then once we've added them, which is a really quick process, this is very fast few-shot learning, we can evaluate its performance. So here we can see that these are the top 5 predictions for our 3 different models, given this new, never before seen input image based on only 5 training samples. And we can also assess its accuracy over the entire data set that we collected, which was 20 extra images, and it achieved an accuracy of 100%, which means the model worked quite well. Now that we've seen a demonstration of how our model works, to evaluate our model, we have both quantitative and qualitative metrics. Our most important quantitative metric that we used to evaluate our model was validation and test accuracy. While the accuracy on the slide seems quite low at first glance, keep in mind that the random guessing will have a test accuracy of 0.1% since there are 1,000 classes. We trained a baseline model, which obtained a test accuracy of 0.5%. We also tested using untuned networks using our ensemble, which obtained an accuracy of 14%. Our tuned model has a test accuracy of 19.6%, which outperforms both the baseline and the untuned models by a significant margin. Here is an example of a more qualitative result. The sample was randomly selected from our training set as an illustrative example of our model's potential. As you can see, the predictions are somewhat reasonable. This concludes the showcase of our model. Thank you so much for listening to our presentation.